Okay, so let's go ahead and get started. So last time I made the claim that any attempt to incorporate special relativity into quantum mechanics will automatically lead you to theories where you have multi-particle states. So we saw one example of that last time. So the general slogan is that quantum mechanics plus special relativity means that you necessarily have multi-particle states. And today what I would like to do is to continue to flesh out that relationship between special relativity and the existence of multi-particle states and the necessity of allowing particles to be created and destroyed. And in particular, what I'd like to do is just spend a few more minutes at the beginning of class today finishing up with Dirac's construction of a theory of multi-particle states. So just to remind you, Dirac's idea was that we should study the single particle wave function, or the single particle Schrodinger equation, in quantum mechanics. So that's minus I h bar d by dt of psi is equal to p squared plus m squared, the square root of that, times psi. So this, of course, is just the expression for energy in special relativity. Again, using units where c and h bar is equal to 1. And that we should find some operators, matrices, alpha and beta, which we constructed last class, such that we can actually take this square root and find an equation which treats space and time democratically in the sense that the right-hand side of this equation is linear in d by dx. So this, of course, so p, of course, is the derivative operator, d by dx. So this is minus I alpha times the gradient plus beta times m acting on psi. And the point of this equation is that it treats, and there's no minus sign here. Okay, you guys have to keep correcting me. When I do things like write down Schrodinger's equation incorrectly, that's the sort of thing that it's your responsibility to remind me to do correctly. Okay, so Dirac's equation treats space and time democratically, but we saw last class that it really only works for particles with spin 1/2. So in particular, the simplest example of these alpha and beta matrices were the 4x4 matrices that I wrote down for you last class. So alpha is 0 times the Pauli matrices in the off-diagonal elements, writing the 4x4 matrix alpha in 2x2 block form, and beta, well, it's this diagonal matrix. So this was the simplest example of a Dirac equation, which describes the dynamics we saw last time, or I told you last time, of spin 1/2 particles, such as electrons And we found the solutions of this equation last time in terms of plane waves. And one of the things that we saw was that there were both positive and negative energy solutions, which led Dirac to postulate the existence of the Dirac sea, just meaning that all of the negative energy states were filled up, and all of the positive energy states, at least in the vacuum, were unoccupied. And then if we start coupling this theory to other systems, let's say we add electromagnetism or something like that, then that would allow for the possibility of one of these electrons in a negative energy state to hop up to a positive energy state, which would create a hole in the Dirac sea, and that hole could then be viewed as another fundamental particle, an antiparticle, which has positive energy but exact opposite properties in all other respects from the original particle. So for example, if these electrons have negative mass, then a hole in the Dirac sea is an absence of something with negative, if the electrons have negative charge, then a hole in the Dirac sea is the absence of a negative charge, that is to say a positive charge. There's a question.
Is it important your beta 1 minus 1 or not some 1?
Oh, that's not important. Did I write it last time as 1 minus 1? Okay. That is not important, but I will write it that way if that's why I wrote it last time. Okay, and so this was an example of the case where a way where we try and write down theories of quantum mechanics that are consistent with special relativity, and we automatically end up with multi-particle states, and we automatically end up with a theory where particles can be created or destroyed. Okay. What I'm going to do for the rest of class today is describe two other attempts to unify quantum mechanics and special relativity, and we'll see that both of these other ways of unifying special relativity and quantum mechanics also lead to multi-particle physics, and that will naturally lead us to quantum field theory. Okay. But before I do so, I can't resist just pointing out one more really interesting feature of the Dirac equation. And really, this is something that we'll be returning to and spending a lot more time on later on in this semester. But it's something that I want to bring up now because, okay, this is the first week of quantum field theory. Part of my goal here is to convince you that quantum field theory is interesting and worth studying. So what I'd like to do is talk about how the Dirac equation can be used to make predictions about the internal structure of the electron. And this will set us up for some computations later in the semester when we study quantum electrodynamics. But the very basic predictions of the Dirac equation and special relativity for the internal structure of the electron can already be seen from the Dirac equation that we've written down so far. Okay. Before I do that and go into that, let me just pause and see if there are any questions. Okay, great. So to study the Dirac equation in a little bit more detail, what I want to do is remember that the particle that I'm trying to describe here, an electron, has electromagnetic charge. And so what we would like to do is couple this to an electromagnetic field. That is to say, an E field and a B field. And so what we want to do is take this Schrodinger equation here, this Dirac equation that I've written, and figure out how it is that we can couple this to an electromagnetic field. Okay. So we should remember that an electromagnetic field in quantum mechanics, well, and even in electromagnetism, is most easily described in terms of a scalar and a vector potential. So the scalar potential, I'll denote phi. So the electric field is the gradient of the scalar potential. The vector potential I'll call A. The magnetic field is the curl of the vector potential. And when you're coupling a quantum mechanical system, a particle, to this electromagnetic field, then it's very simple. The way that you do that is simply you take the momentum appearing in Schrodinger's equation and you replace it by P minus Q times A. So that's how you couple a particle to a magnetic field. And to couple a particle to an electrostatic field, you include the potential by just setting the V in Schrodinger's equation, H is P squared over 2m plus V, to be equal to phi, or Q phi. And that's just the statement that the electrostatic potential gives you a potential energy that's Q times the electrostatic potential. So that means that the Dirac equation, describing a particle propagating in an electromagnetic field, should look something like this. So we have the usual Dirac equation, simply with the modification that P has become P minus Q times A, and I've also added the contribution of the electrostatic potential. And what I'd now like to do is imagine that we just have an electron here coupled to a magnetic field, so that we can set the electrostatic potential equals to 0. Okay. And let's ask if we can reproduce the usual non-relativistic Schrodinger equation in the limit where the momentum is very small. So can we reproduce the usual Schrodinger equation in the non-relativistic limit. Okay. So just to make the notation a little simpler, I'll take this combination P minus QA and call it pi. And then what I'd like to do is consider those plane wave solutions that I wrote down for you last time. So the plane wave solutions were of the form psi was equal to some, I guess I called it W, some, I guess I'm using phi in two different places here. It was equal to some 4-component vector, which I wrote in 2-component notation as chi over phi, where chi and phi are just 2-component column vectors, times e to the I p dot x minus et, or did I call it omega t? Let me just check and make sure I'm using the same notation that I did. I called it e. Minus et, where e is the energy of the system. And in order to take the non-relativistic limit, I'd like to consider these solutions when the energy is very close to its rest mass. That is to say, the momentum of these particles is very small. So the energy will be mc squared, which is the rest mass, plus some small quantity epsilon. And what is epsilon? Epsilon is the non-relativistic energy, p squared over 2m. And so remember that when we wrote down the Dirac equation, we had, so the Dirac equation last time was the statement that E minus M times minus sigma dot P, so that'll be replaced by a pi now because we're studying the Dirac equation in the background of a magnetic field. This 4x4 matrix acting on that column vector chi phi should be equal to 0. So let's now go ahead and analyze this to leading order in epsilon when epsilon is very small. Okay. So that top equation, so E minus M is just epsilon. So that top equation says that epsilon chi is equal to sigma dot pi times phi, and then using the lower equation, sigma phi is equal to 1 over E plus M, which is M to 2M to leading order in epsilon, times sigma dot pi times chi. So that's sigma dot pi squared divided by 2m times chi. Okay. So let's just work this out in a little bit more detail. So this is supposed to be this equation that I've written here, epsilon chi equals sigma dot pi over squared over 2m chi. That is supposed to be the usual non-relativistic Schrodinger equation. So let's work that out in a little bit more detail to see how that works. So here I'm going to remind you of the following algebraic identity. So it's a good name for a vector. Okay, I'll call a vector A here. So let me just remind you of the following algebraic identity for Pauli matrices. So this identity that I'm writing down here is just a fancy way of packaging the algebra of Pauli matrices. And so if you look at this equation, so if you're not familiar with this equation, then you should definitely prove it to yourselves. So this is just another way of rewriting the usual product rule for Pauli matrices. Sigma x times sigma y is sigma z, sigma y times sigma z is sigma x, and so on and so forth. Okay. So this, and sigma x squared is equal to 1. So this is just another way of repackaging that algebra. So if you went ahead and plugged tried to evaluate this expression up here by using the Pauli matrix algebra, then you might think that you would just get a pi squared term coming from here, and you would almost, but not entirely, be correct. Okay. So in particular, what's pi cross pi? So where pi, again, is p minus qa, p here being the momentum operator, and a being this background magnetic field. Well, usually, of course, a vector cross itself is equal to 0. But this vector here is not a vector of numbers, it's a vector of operators. Okay. And the fact that a vector cross itself is equal to 0 followed from the fact that the numbers that make up the vector commute with one another, but operators don't commute with each other. So in fact, it's not true that a vector's worth of operators cross itself is equal to 0. Okay. So let's go ahead and work out what this is. So, by the way, have you guys all seen Einstein summation notation? Raise your hand if you have not seen Einstein summation notation. Okay. So I'll give you guys at some point a very brief introduction to Lorentz invariance, special relativity, Einstein summation notation. But for now, I'll just use this summation notation and tell you exactly what I'm doing as I do it. So we can just use the expression for the cross product in Einstein summation notation. So the cross product pi cross pi is epsilon ijk, pi j, pi k, where I'm using the Einstein summation notation where I'm summing over j and k from 1 up to 3. And have you all seen the fact that a cross product can be written in terms of the epsilon symbol? Okay. If you haven't seen that, you should have, well, you can go remind yourselves of it. I guess you learned about it in electromagnetism or something like that. So let's go ahead and work that out. So that's epsilon ijk times pj minus qaj, pk minus qak. So of course, the term where you have a pj times a pk is equal to 0, and likewise the term aj times ak is equal to 0, because when you contract it with the epsilon symbol, that guy's antisymmetric in all of its indices, so that'll just give you 0. But you're left with something non-zero, which is q times epsilon ijk times pj, well, I'll pull out an IH bar and write it this way, times the derivative with respect to xj of ak minus the derivative with respect to xk of aj, otherwise known as minus iq, times the curl of a, or rather the ith component of the curl of a. And what's the curl of a? It's the magnetic field. So pi cross pi is IQ times the magnetic field. So if you use this expression, and so to evaluate the equation that I've written up here, you have epsilon times chi is equal to, that first term is just p minus qa quantity squared over 2m, and that second term is going to be q over m times sigma dot b. So what is this? So the usual Schrodinger equation says that the Hamiltonian is equal to p squared over 2m, or p minus qa squared over 2m for a particle in a magnetic field. So this is the usual kinetic term in the Schrodinger equation for a particle in a magnetic field, in the non-relativistic limit. And what we found here is that there is an extra term, sigma dot b, which describes the specific interaction of a spin 1/2 particle that carries charge with an external magnetic field. And in particular, what this extra term is telling us is it's telling us the magnetic moment of the electron. So what we've seen here is that the Dirac equation, derived just by coupling quantum mechanics to special relativity, makes a specific prediction for the magnetic moment of the electron. Just by considering special relativity and quantum mechanics together, we've predicted exactly the size of the interaction here, that coefficient that tells you about the coupling of the spin of an electron to a magnetic field. So typically when we talk about, is there a question? Yes.
B is just curly, right? There's no negative sign.
Yeah, did I introduce a minus sign somewhere?
Yes,
Okay.
what happened was between the last.
Did I, yeah, is there not a minus sign there?
I'm not sure.
Okay. So there's a minus sign because P is minus IH bar d by d. So that minus sign is okay. Is there an I somewhere? There were two I's that multiplied together. Okay. Let's not nitpick over details like this, because this is supposed to be just an aside for some motivation. You know, if you want to know what the Dirac equation is, you can look it up. Okay. I think I got all the signs right. There was a couple. I did some algebraic simplifications. There was an I times an I. There was a minus sign coming from the IH bar d by dx. If I got a sign wrong, I'm not going to lose any sleep over it. I have a job. I don't need to get signs right anymore. But you guys can all. You guys need to get the signs right, so you can go ahead and do that on your own time. Okay, good. When we talk about the magnetic moment of a particle, we typically characterize that in terms of what's known as the G factor. Okay. So an object with angular momentum J will interact in general, let's say a charged object. So a charged object carrying some angular momentum, let's just say we have a charged sphere, for example, that we put at some finite angular momentum by spinning it around, that'll interact with a background magnetic field. Via some interaction of the form the magnetic moment dotted with B, which will be something that we usually call G times Q over 2m times the angular momentum dotted with B. Okay. So the interaction of an object with a magnetic moment mu with a background magnetic field is given by the Hamiltonian mu dot B. That's just what a magnetic moment means. And then if you imagine that this magnetic moment comes because you have a charged object that's given some angular momentum, then you should always be able to write this as J dot B times some coefficient. And I've just pulled a factor of Q over 2m out of that coefficient just sort of really as a definition, so that we're left with some dimensionless constant here. Known as the Landé G factor. Okay. And what we see is that, so here we have Dirac's equation for a spin 1/2 particle. And so remember that for spin 1/2 fields, the angular momentum, J, is h bar over 2 times sigma.
Connect to the internet.
Oh my. Okay.
Not available. Connect to
that
the
my
internet.
phone? Sorry about that. So you can see then that Dirac's equation makes some specific prediction for the magnetic moment of the electron. So Dirac's equation says that G is equal to 2. Now, if you just had a charged sphere, so if you just took a solid sphere that carried some charge that was uniformly distributed over the sphere, you gave it some angular momentum, then for that charged sphere, G would be equal to 1. Okay. That's why we introduced that factor of 2 here, so that for a charged sphere it would be equal to 1. So what we're seeing here is that we've made some very special prediction for the magnetic moment of the electron, for some piece of the internal structure of the electron. Okay. And later on in this course, and this will be one of the goals of the first semester of this course, by studying further corrections due to the interactions of the electron with electromagnetism. So by considering the corrections due to quantum electrodynamics, we will show that in fact this will get corrected. So for example, the first leading correction is something we'll compute later on in the course. It looks like this, where this dimensionless ratio here, q squared over h bar times c, is known as the fine structure constant. It's a small number. It's about 1 over 137. So that, in fact, the leading answer that we've derived here, G is equal to 2, is actually pretty good to a few decimal points. Okay. And so, in fact, the computation of the anomalous magnetic moment of the electron in quantum electrodynamics is considered one of the great successes, really the first great success of quantum field theory. Okay? And that's really what we're going to be shooting for as our first main goal in the first part of the course. And in fact, one can compute, although we're not going to do it in this class, further corrections to the magnetic moment of the electron. Okay? So in fact, theorists have worked very hard, this is just for your cultural knowledge, to compute the corrections to the anomalous magnetic moment of the electron. I believe that the state of the art is going to sixth order and perturbation theory. And the anomalous magnetic moment of the electron is perhaps the most precisely studied number in physics. It's known to a fairly high degree of accuracy. And so what we have here is a match between theory and experiment to 1 part in 10 to the minus 12. Okay. So I think it's fair to say that this is one of, if not the greatest match between theory and experiment in the history of physics. Okay. And in fact, although at leading order, the leading correction to the anomalous magnetic moment of the electron only requires quantum electrodynamics, all of the various subleading terms involve much more complicated physics because once you study these things in more detail, other things, more complicated particles, will contribute to this anomalous magnetic moment. And it's also interesting to note that the theoretical answer has more uncertainty than the experimental result. This is a case where the experimentalists are ahead of the theorists. And interestingly enough, the primary theoretical error comes because we can't do the integrals. Okay. Because this is, in the language of Feynman diagrams, I forget where this is a 5 or a 6 loop Feynman diagram correction. It involves horrible integrals that can only be done numerically using Monte Carlo method. And so, in fact, the primary obstacle is just doing the damn integrals. And that'll be a primary obstacle for you in this course as well. Okay, good. So we've seen that Dirac's theory of the electron, based on single particle quantum mechanics, is in some ways a great success, but in other ways, Dirac's theory is a bit of a disappointment, in particular because it works only for fermions. Remember that the Dirac sea was necessary in order to get rid of, to fill up all of the negative energy states so that the ground state, the vacuum state, would be stable. That requires fermions. For bosons, of course, we have no idea how to do that. And, of course, in some sense, the first quantum field theory that we should all be worried about is the field theory of electrodynamics. Indeed, Planck's original discovery of quantum mechanics, or at least aspects of quantum mechanics, was actually a consideration of the dynamics of electromagnetism in a box, blackbody radiation. And in fact, that was a study not of quantum mechanics, but of quantum field theory. Okay? And so, for example, if you're going to resolve the ultraviolet catastrophe, as Planck did when thinking about blackbody radiation, then you need to be able to study bosonic particles, like photons, the particles of electromagnetism, and not just fermions. Okay. So what I'd like to do now is to move on and try and revisit a few other ways that we could try and approach the unification of special relativity in quantum mechanics, and see inevitably that this will lead us to field theories. Before I do so, let me pause here and see if there are any questions. Everything clear so far? Good. So let's recall our original problem. Okay. So what other approaches could we take to the unification of special relativity with quantum mechanics? Okay. So remember, if we just want to try and study single particle quantum mechanics, then what we're doing is studying Schrödinger's equation. So what I'd like to spend just a few minutes doing right now is seeing what happens if we just literally study Schrödinger's equation with the Hamiltonian given not by p squared over 2m, which is the Newtonian value, but by its value in special relativity. So let's try and study single particle quantum mechanics directly in special relativity. So that is to say, let's study the Schrödinger equation for some wave function where the Hamiltonian is given by p squared, the square root of p squared plus m squared. Okay. So we're not going to do what Dirac did and try and find some funny Hilbert space with spin 1/2 particles where I can take that square, the thing inside the square root, and write it as a perfect square. Let's just try and think about a single particle, a boson, and ask what happens if we try and just solve this wave equation directly. So here, the Hamiltonian is equal to the square root of p squared plus m squared. And so just as if we were working in single particle quantum mechanics in the non-relativistic case, it makes sense to organize the states in our Hilbert space in momentum eigenstates. So let's use momentum eigenstates. So in particular, the state k will denote some state with momentum eigenvalue k. And so that h on the state is just what I will call omega sub k times k, where omega sub k is the energy in special relativity of a particle with momentum k. So my claim is that this theory of single particle quantum mechanics, where we just take the momentum eigenstates and instead of the energy of the state with momentum k being k squared over 2m, I let the energy be the square root of k squared plus m squared. I claim that this is a deeply sick theory. And so let me show you exactly how sick it is. So let's calculate the probability, or the quantum mechanical amplitude, for a particle in this theory to travel from, say, the origin x equals 0 at time t equals 0 to a position x at time t. So how would we do this in quantum mechanics? Well, we would start with the state where x is equal to 0. We would use the time evolution operator, e to the minus I ht, to evolve forward in time by an amount t. And then we would project onto the state where the particle is at position x. So here, this is a position eigenstate. Okay, so what is that amplitude? Well, because the Hamiltonian is diagonal in momentum space, this is going to be easiest to calculate if we insert a complete basis of momentum states. So this is the integral d3k of xk times k times e to the I ht acting on the state where x is equal to 0. So here all I've done is insert a complete basis of momentum states right here. I haven't actually done anything. Now we can rewrite this a little bit. So what is this guy right here? Well, this is just the wave function in momentum space. So this is e to the I k dot x. So that's just the, well, that's either the x wave function in momentum space or the momentum space wave function in x space, however you want to talk about it. It's the wave function of a particle with momentum k. And what is this guy here? Well, we know that h is diagonal in momentum space. So this is e to the minus I omega sub k, the eigenvalue of x, times t, times the wave function of the state where x is equal to 0 in momentum space, which is just 1. So we just need to do that integral. So let's just go ahead and do that integral and see what sort of answer we get. Okay. Everything clear so far? Everyone with me? Good. So let me let me do this integral in spherical coordinates. So I'll let the vector k, so let's just choose a coordinate system where, say, x is located on the z-axis. So r is the distance between x and the origin. So x will be somewhere on the z-axis. And then I'll go to polar coordinates where k is the norm of the vector k, and theta is the angle of the vector k off of the z-axis. So then we can rewrite this integral in spherical coordinates. So we first have to do the k integral. So it's the integral of k squared dk from 0 to infinity. Then we have to do the theta integral from 0 to pi of d theta sine theta. And then we have a phi integral, where phi is the other angle, from 0 to 2 pi, so that the azimuthal angle. And then we have our integrand, which is e to the I. So I k dot x is I kr cosine theta, and then minus omega k times t. Everyone with me so far? So the phi integral just gives me some factor of 2 pi. I'm not going to worry about factors of 2 pi here because the answer that we get is going to be nonsense at the end of the day. Let's do the theta integral. So d theta times sine theta is otherwise known as d of cosine theta. And integrating theta from 0 to pi means that you take cosine theta to run from -1 to 1. So you can just do the phi and theta integrations. So we're integrating d of cosine theta of e to the I kr cosine theta. So what does that get you? Well, it gets you a factor of 1 over kir. So we get a 1 over IR, 1 over IR out front, and we lose a factor of k. So of e to the minus I omega kt, and then we have to evaluate the e to the I kr cosine r at either side of the range of integration. Okay, so let's stare at that for a second. So that's still a sort of hard, tricky integration to do. So let me just remind you that omega k, so I don't want to do that integral explicitly, but I just want to explain one of its properties to you. So in particular, what we're interested in doing is studying this integral when r is bigger than t. Remember, we're using units where the speed of light is equal to 1, and we're studying the amplitude for a particle to move from the origin at time t equals 0 to a distance r away at time t. So when r is bigger than t, that means we're asking that the amplitude for this particle to travel faster than the speed of light. So i.e., r is bigger than ct, so that the point that the particle travels to is outside of the light cone of the original point. So we can actually do this integral. I'm not going to actually do the integral for you. I'm just going to argue for you that it's strictly non-zero, okay, which will mean that this particle can travel faster than the speed of light. So the argument that I'm going to give to you is the following. Okay. So let's imagine doing this integral dk in the following way. Okay. What I would like to do is rewrite this as 1 over IR times the integral of k from minus infinity to infinity, k dk. Here, I'll write it down. So that integral is 1 over IR times the integral from minus infinity to infinity, k dk, of e to the I kr minus I omega k, so that's minus I times the square root of k squared plus m squared times t. Well, all I've done here is I've noticed that these two different terms, that this second term can be interpreted as that first term, where the integrand is taken to be negative instead, where the k is taken to be negative rather than positive. So I've just sort of written those sum of two terms as a single integral over a larger range. Now I want to do this integral by thinking about it as an integral in the complex k-plane. Okay. So what does this integrand look like in the complex k-plane? So in the complex k-plane, we're doing the integral along the real k-axis here. And the integrand is a perfectly nice analytic function in the complex k-plane, except that it has a branch cut at a point where k is equal to I times m. So, in particular, that's the point where that square root has a branch cut. And when r is bigger than t, the integral vanishes when the absolute value of k goes to infinity for positive imaginary part. So that means that we could do this integral by deforming the contour to go all the way up here. So that's supposed to be large absolute value of k with positive imaginary part. And you can do the integral, so you can deform the integral so that it goes up there. And all you have to do is take into account the fact that it'll pick up something as you go across the branch cut. Okay. So you have to deform it to go around the branch cut. You guys have all seen this, presumably, in your this sort of trick before in your complex variables class. So what that means is that we could rewrite this integral just as an integral along the branch cut. Because the integral out here at infinity is out here, the integral vanishes. So you only have to worry about the contribution to the integral when you integrate along that branch cut. And what's the answer? So this amplitude, well, you get a 1 over IR. We have to integrate along the branch cut. So along the branch cut, I'll let k equal to I times some variable z. Okay. So this k dk becomes a z dz. And z gets integrated from m up to infinity. So the branch cut starts when k is equal to im. And then we get the integrand. Okay. And you have to take the two sides of the branch cut. So on the left-hand side, you get e to the z squared minus m squared times t. And then on the other side, you get an e to the minus z squared minus m squared times t. And the point is that these two guys combine together into a sinh of the square root of z squared minus m squared times t, which is a positive definite quantity because z is bigger than m. So what we get is that the amplitude is the integral of some positive definite quantity, and so in particular, it's going to be non-zero. So what does this mean? What this means is that if you have a single particle theory where we use the Hamiltonian of special relativity instead of the Hamiltonian of Newtonian mechanics, you can travel faster than the speed of light. That if I try and send a particle, there's some non-zero probability that a particle can move faster than the speed of light. And moving faster than the speed of light in special relativity is bad because it means you can go back in time and kill your grandfather. So in particular, in special relativity, moving faster than the speed of light in one reference frame looks like going backwards in time in another reference frame. So there is a non-zero probability that a particle can move faster than the speed of light. Which, of course, is the same as going back in time. So you can't have a single particle theory of quantum mechanics in special relativity without violating causality. Question in the back.
Can you do a similar computation in the non-relativistic Hamiltonian and get zero?
Yes. Sorry, no. I didn't answer your question correctly. For a non-relativistic Hamiltonian, you'll get a finite answer, but that's because you're using the wrong Hamiltonian. Let's put it this way. You will get a finite answer, but that's okay because it was an answer computed using Newtonian physics in a case where you should have been using special relativity. If you understand what I'm saying. I thought you were asking a different question, but yes.
In the other cases,
yes.
You don't mind if it goes faster.
In the other case, you don't mind if it goes faster than the speed of light because you're not studying special relativity. In particular, you know that you can't use that Newtonian physics to study cases when particles go faster than the speed of light. And by the way, I've used this fancy sort of contour argument because this is the kind of thing you're going to need to get used to because we're going to use it a lot. Right? And in fact, the argument that I've given here has a flavor for a lot of arguments that we'll be giving on later in this class. Question in the back.
This you have, but with the Hamiltonian being
Yes, excellent. Okay, we are going to do that, actually. So in particular, one of the things that we'll be doing, so what I'm calculating here is a propagator. Okay, a propagator is a fancy name for the amplitude for a particle to travel a certain distance in a certain amount of time. And what I've proven for you is that the propagator of this single particle relativistic theory is acausal. One of the things that we're going to do is then revisit these, when we come back and study these in a week or two using quantum field theory. We'll calculate these again, and we'll see that these are in fact perfectly causal and perfectly vanishing when they're supposed to be vanishing for good relativistic theories. And a Dirac particle is one of the particles that we'll study. But we'll start out with simpler things, actually. So keep this computation in mind, because we're going to redo it in a few weeks when we study the propagators of free scalar field theory. Question?
Have you ever ruled out this idea by checking the equation of motion for Lorentz invariance?
The equation of motion for Lorentz invariance.
Placing P and Q equal.
Okay, I believe, I don't think so. Yeah. Okay. Yeah, okay. Good. Any other questions? Okay. So, this problem really arose because we were taking a square root, and because we had this branch cut in the Hamiltonian. So, the question that we now want to ask is, could we have avoided this somehow? So how could you avoid having an evolution equation like this where you have a square root and where you have this branch cut that's giving us all of these problems? Well, Dirac gave us one way of avoiding it. That was to consider a spin 1/2 particle where you can take the square root, you don't get a branch cut. Then you had other funny things going on. But a different thing that we could try is we could try replacing the usual Schrodinger equation, so I h bar d by dt of psi is equal to the square root of, let's call it m squared plus p squared acting on psi, or let me write it out more explicitly, m squared minus the gradient squared acting on psi by the square of this equation. So in particular, instead of taking the first derivative of psi, you take the second derivative of psi. So what we're doing is we're now imagining that we have some new version of the Schrodinger equation where we take a second derivative. So you act with two time derivatives. And that has the effect of getting rid of that square root. Okay. So we have the equation of motion minus h bar, which is equal to 1, squared d by dt squared on this wave function that depends on position and time. Here, let me write it this way. So minus d by dt squared plus grad squared acting on psi of x and t is equal to m squared psi. Okay. So this is a perfectly reasonable alternative to the Schrodinger equation. It's a very important equation. This is known as the Klein-Gordon equation. And it is the natural analog, or the natural generalization of Schrodinger's equation to special relativity. In fact, Schrodinger, when he was trying to develop his theory of quantum mechanics, discovered the Klein-Gordon equation before he discovered Schrodinger's equation. But he never published. Okay. And if you don't publish, nobody remembers you for anything. Okay. But, in fact, there's a reason why Schrodinger never published. And the reason why Schrodinger never published is that if you consider this as an equation of motion for a quantum mechanical wave function, then it makes no sense. Why does it make no sense? So, in particular, as an equation for a quantum mechanical wave function, you could consider, say, the probability that a particle is at a point x at time t, and you could integrate this dx. So this, what is this? This is the probability that the particle is somewhere at time t. And it better be equal to 1. And in particular, this quantity better be time independent. But if you have a wave function that obeys a second-order differential equation in time rather than a first-order derivative in time, then there's no reason why this probability should be constant. So in the case of the Schrödinger equation, where you took one derivative with respect to time, then it's easy to check, and if you don't remember how this goes, you should do so. It's easy to check that this quantity that I've written here, if you just plug in the Schrödinger equation, you integrate by parts, that's something that is constant in time. So if it's equal to 1 at time t equals 0, it's equal to 1 for all times. Okay. But if we interpret the Klein-Gordon equation as an equation for a quantum mechanical wave function in the sense of Schrödinger, then probabilities are not conserved. So probabilities are not conserved. So that means that this Klein-Gordon equation can't be interpreted as an equation for the quantum mechanical wave function of a particle. But, as we will see in just a few minutes, it still has a very important and interesting interpretation. It's just a slightly different one. So whatever quantity it is that obeys the Klein-Gordon equation, it better not be the wave function of a particle, because that would make no sense. In particular, it better not be the thing that if you square it gives you the probability that a particle is at a particular position. Okay. So maybe we should step back a second at this point and ask really why it is that we're having so much trouble coming up with theories of quantum mechanics that are consistent with special relativity. Okay. And the basic problem that we're having is that in quantum mechanics, as we usually formulate it, space and time are treated very differently. So in particular, space, that is a position of something in quantum mechanics, is an operator. So there's an operator that measures the position of a particle if you're studying a particle in quantum mechanics. And so it's some sort of observable. But time is not an operator. It's not an observable. Instead, it's a label. Time is a parameter that is used to label operators. That is to say, it's something that is used, it's a parameter used to label the observables of your theory. So if you want a theory that really treats space and time democratically, then you need to resolve this, and you need to change the way that you think about x and t. So one thing that you could do is you could try and come up with a formalism where time is an operator just as x is an operator. And that actually does lead you to a formulation of quantum field theory. But instead, what I'm going to do is I'm going to propose that if time is used to label operators, then x should be used to label operators as well. So to treat x and t democratically, we should consider a theory where the observables, that is to say the operators in the theory, are labeled not by time, but by time and space. So what we're looking for is a theory where the observables, so a typical observable might be something that you call phi, is actually a function both of space and time. So we have names for theories where the observables are functions of space and time. We call them field theories. And an observable that's a function of space and time is called a field. So roughly speaking, if you think about this in the language of quantum mechanics, there is 1 degree of freedom per point in space-time. Or sometimes we say that this would be a theory with 1 local degree of freedom. So we have some reason to suspect that the only theories that can be made consistent with special relativity are those where the observables come with 1 for each point in space-time. And in fact, you are already intimately familiar with at least one example of a field theory, actually several examples of field theories. So the prototypical example is electromagnetism. So in electromagnetism, you have an electric field and a magnetic field, which are functions of position and time. And those are observables. You could observe the electric field at a given position and time. You could observe it at a different position and time. And there's a whole infinite family of observables, 1 for each possible spatial position and time. Sometimes it's more convenient to talk about electromagnetism in terms of a vector and a scalar potential. So in terms of the potentials, phi and A, it's often convenient to talk about electromagnetism phrased in terms of a single object that we call the electromagnetic gauge field. And what is that? That's just the set of 4 objects. So mu here is an index that runs from 0 up to 3. So A sub 0 is equal to phi. A sub 1, A sub 2, and A sub 3 are just the usual vector potentials. So I don't know if you actually, did you see this in your electromagnetism class? Okay. So in electromagnetism, this is a particularly economical way of packaging the dynamics of the electromagnetic field. If you haven't seen this, don't worry. You'll get plenty of practice manipulating it on your problem sets. So why do I bring up the example of the electromagnetic field? So as you know, the electromagnetic field obeys some classical equations of motion, known as Maxwell's equation. Those are first-order differential equations for E and B, and second-order differential equations for the components of the gauge field. Okay. So for example, there's a phi, the vector potential, obeys a second-order equation. What is that equation? That equation is the Klein-Gordon equation. So each component of the electromagnetic potential, or so the electromagnetic 4 vector, A mu, obeys the Klein-Gordon equation. So in particular, minus d by dt squared plus the gradient squared of A is equal to 0. And this is the Klein-Gordon equation that I wrote above with 0 mass. Now, in your class in electromagnetism, you didn't call this the Klein-Gordon equation. You probably called it the D'Alembertian equation or the Poisson equation, but it's the same thing. Okay? The wave equation. It's, there's lots of different names for these sorts of things. I guess the Poisson equation is the one in Euclidean signature. The D'Alembertian is what you call it when you write it with a minus sign in Lorentzian, with the minus sign in the time direction. Okay? Or you just call it the wave equation. Okay. So I really want to make clear that there's an important distinction between this appearance of the Klein-Gordon equation and the appearance that I talked about a minute ago. Okay. So we saw that the Klein-Gordon equation makes no sense as a wave equation for a quantum field in single particle quantum mechanics. But now we see it does make sense as a classical equation of motion for some field. So this then is the program that we're going to be following really for the rest of this course. So we're going to be studying the dynamics of fields such as those that obey the Klein-Gordon equation, as a classical equation of motion, as their classical wave equation, and then we're going to quantize them. So, there's a sort of name that people use when they talk about this procedure of studying a classical field and then quantizing it. Sometimes people call this second quantization. The reason being the following. First quantization is what you learned in your quantum mechanics classes. It's where you take your wave function and you do all the usual things you do with a wave function. Okay. You think about the wave function as the space of wave functions is giving you a Hilbert space, and the observables are operators on that Hilbert space. People call what we're doing now second quantization because you start out with something that itself obeys a wave equation, something that obeys a Klein-Gordon equation, for example, and you view that not as the wave functions that give you a Hilbert space, but you view that as the classical observable, as the set of operators, and then you need to find the Hilbert space on which those act. So it's sort of like you're taking a wave function and then you're quantizing it again. Now that's a terrible language because as you know, the vector potential or the scalar potential of electromagnetism is not a quantum mechanical wave function. It obeys a wave equation, sure, but that's just its classical equation of motion. So the distinction between first quantization and second quantization is kind of just like an artificial trick, or it's just like some artificial language that is not very illuminating, but people use this name all the time, so you should know it. Okay, so just to summarize, what we want to do is study the procedure known as second quantization, where a classical field, let's call it phi, becomes an operator. In the same way that in usual first quantization, you study the procedure where the position of a particle, for example, will become an operator. Okay. And so the questions then that we need to answer are, well, what is the physical space of states on which this operator acts? What is the Hilbert space? And why does it describe multi-particle states? In particular, why does it describe dynamics where you can have particle creation or destruction? So we're really at a point where we can now dive in full glory into quantum field theory. Maybe I should pause here and see if there are any questions. No questions? Everything clear so far? For my information, has the pace that I've been going at been too slow, too fast? Okay. If you're embarrassed to say that it's too fast or too slow, you should not be. Has it been perfect? Okay, good. Okay. Yeah, if I'm going too slow, feel free to let me know and I can speed up. Likewise, if you want me to go over something again or in more detail, let me know and I can try and do that too. Okay. So, let's see. We've got about 10 minutes left. Okay. And the final point that I want to make, in our sort of introduction to quantum field theory, which is really what we're doing this week, is I want to explain precisely what the relationship is between our field phi and the fact that our theory has multi-particle states. So what precisely is the relation between a field theory, that is to say a quantum field theory, a theory where you regard this classical field as an operator on some quantum mechanical Hilbert space, and multi-particle dynamics? So I've argued for you that single particle dynamics and special relativity doesn't work. I've argued for you that a field is necessary in order to write down a theory that is consistent with special relativity. But what is the precise relationship between this field, say this field phi that I described above, and the fact that the theory has multi-particle states? So to try and answer that question, what I'd like to imagine doing is the following. Let's just try to directly construct a multi-particle theory in quantum mechanics. Okay. And actually, for a lot of what I'm going to say now, one doesn't even really need to assume special relativity. So let's try and directly construct a quantum mechanical theory describing a bunch of particles where we're allowed to create and destroy particles. So what should the Hilbert space look like? Well, the Hilbert space should contain a state with no particles. Okay. So the Hilbert space should contain the following states. So it should contain a state with no particles. I'll call that the vacuum state. It should contain states with one particle. And I'll denote by K a state where you have a particle with momentum K. It should have states with two particles. And in this case, to specify the state, I'll need to specify two momenta that I'll call K1 and K2, and so on and so forth. Yes? Now I'm just going to talk about a free theory. That is to say, I'm going to talk about a theory where there's no interactions. So let's try and construct, let's say, a free, that is to say, the simplest possible multi-particle theory, just so that we can understand what the relationship is with the fields that I introduced to you earlier. So what does the Hilbert space look like? Well, the Hilbert space is the Hilbert space that you get when you allow arbitrary superpositions of the no particle state, the one particle state, the two particle states, and so forth. if you want to use fancy language, the Hilbert space is the direct sum of, say, the Hilbert space of the no particle state that we could call H0 with the one particle states and the two particle states and so on and so forth. So a state can then be an arbitrary linear combination of linear superposition of n particle states for any number n. And this Hilbert space, where we just have this free, non-interacting set of all possible particle states, is known as Fock space. And in fact, Fock space, it turns out, is a Hilbert space that you've studied many times before. You know it and love it. It's the most famous quantum mechanical system. It's the harmonic oscillator. Okay? It's just an infinite number of copies of them. So let's see why that is. So in order to understand in a little bit more detail why it is that this is related to a harmonic oscillator, let's just define the operator AK dagger as the operator which creates a particle with momentum k. Okay. So what do I mean by that precisely? Well, I mean that if you start with a vacuum state and you act on it with this operator, you get the state k. And if you act with two of these operators, say A sub k1 and A sub k2, then you get the two particle state, and so on and so forth. Now similarly, AK without the dagger will be the operator which removes a particle with momentum k. So, for example, AK acting on the vacuum, well, that doesn't have any particles. That'll just give you 0. That's my definition of AK. If you try and act on the one particle state, so let's call it, so AK is the operator that tries to remove a particle with momentum k. So let's say you act with AK on the state k prime. That should give you the vacuum state if k is equal to k prime and 0 otherwise. So we should get a delta function. K is equal to k prime times the vacuum state, and so on and so forth. And now let's just think about what algebra it is that these creation and destruction operators should obey. Well, if you think about it, if you look at this equation here for a second, that equation tells you that AK1 dagger should commute with AK2 dagger, at least if these objects are bosons. If you create a particle with momentum k1 and then create the particle with momentum k2, you should get the same thing if you do it in the opposite order. And if you think about it for a second, the fact that I have defined the destruction operators in this way means that AK and AK dagger should commute unless their indices are equal. So in particular, the non-trivial commutation relation is that the commutator of AK with a k prime dagger is the delta function that sets k equals to k prime. So these operators all commute with one another unless k is equal to k prime. And in particular, you hopefully recognize this as precisely the algebra of raising and lowering operators for the simple harmonic oscillator. The only distinction here is that we have an infinite number of them. So we have an infinite number of simple harmonic oscillator raising and lowering operators. One for each momentum k. So in particular, what am I saying here? Well, let's remember what the Hilbert space of a simple harmonic oscillator looks like. The Hilbert space of a simple harmonic oscillator, what is it? Well, it's spanned by a basis that includes the vacuum state, the state with 1 unit of energy, which is a raising operator acting on the vacuum, the state with 2 units of energy, which is the raising operator squared, acting on the vacuum, and so on and so forth. And what we're saying is that our Fock space is the tensor product of the simple harmonic oscillator Hilbert space with one harmonic oscillator for each momentum mode k. By the way, have you seen tensor products before? You did this in quantum mechanics? Okay. I'm not saying anything fancy here. I'm saying the most unfancy thing possible. Okay. All I'm saying is that an arbitrary state is built up. So, for example, a state, say, with 2 particles of momentum k and 1 particle of momentum k prime is given by a k dagger squared times a k prime dagger acting on the vacuum. So I'm out of time, so I have a little bit more that I want to do. What I want to do is describe this Hilbert space to you in a little bit more detail, and then show to you that the natural observables acting on this Hilbert space are precisely the quantum fields that we introduced earlier in this class. I'm out of time, though, so I don't want to do that now. So maybe I can just end by seeing if there are any questions. If any of this is unfamiliar, if you don't remember your harmonic oscillators, if you don't remember your wave equations, if you don't remember your tensor products, you know, the weekend is a lovely time with lots of free time for you to do these sorts of things like read about that. Yes, question?
Are we giving up on normalization, and is it related to the non-conformation?
We're not giving up on normalization. Right now I'm just trying to do a sketchy introduction to this. When I go back and do it in a little bit more detail, I'll insert careful normalization factors. What's that?
So we shouldn't be afraid of that?
Oh, don't be afraid of, no, you should never be afraid of deltas. Okay. So the Dirac delta function here. If we had a finite number of momentum modes, then you would put a Kronecker delta symbol there. But we're taking a continuum limit, and so the appropriate thing to do is to include the Dirac delta. Okay. Nothing fancy there. It just has to do, it's just like, this is just what happens when you have a continuum basis instead of a discrete basis. Okay. If you are not convinced, then the operation that you should do is you should try and consider that your space X is not a continuous space, but rather is a lattice of points, okay, with some distance between them, let's call it epsilon. And then that means that the angular momentum modes will be discretized, will be quantized, okay? And then you would have a Kronecker delta symbol. Then try and take the limit where epsilon goes to 0 in a smooth way so that you reconstruct the continuous number of points on the real number line. Then your momenta will become continuous, and the Kronecker delta will go over to the Dirac delta function, provided that you normalize things with the appropriate powers of epsilon when you take that limit so that everything remains finite. Okay. So often when we think about quantum field theory, in our minds we secretly think about space-time being a little lattice of points, and then we take the limit where that lattice spacing is very small. Good question. Yes?
You said the inlet that there is a consistent relation of quantum
Yeah, that's like the so-called first quantized. Yeah, yeah. There's like a first quantized way of thinking about quantum field theory, where you Yeah, it's a little. Yeah, let's not talk about it. I mean, yes, there is. It's called the. There's a first quantized path integral formulation of quantum field theory, where you compute the amplitude for a particle to move from x to y by summing over all paths, and then then you can really think about the time as a operator in the same sense that the space is an operator. But then you need to introduce some auxiliary parameter to label the points along the curve, and so you end up with. I mean, there's a whole procedure that you can do to treat quantum field theory this way. But that's not the way that it's conventionally approached, and I think it's a little more complicated than what we'll need. But yes, good question. Yes. Oh yeah, I promised a homework. Yeah, I figured that we haven't actually done very much this week, so I couldn't think of enough really hard problems. So instead, I'll give you twice as many next week. Does that sound fair? Okay, great. Yeah, so I'll probably. So what I'll do is, I figured we hadn't done enough for me to really give a good homework, so I'll just give you a homework next week. So yeah, just as far as the timing goes, I'm probably going to try and hand out homeworks on Thursdays and have them due the next Friday afternoon. Is that fine with everyone? Like, I guess there's some flexibility as regards to when homeworks are due, but unless people object, that's probably what I'll do. And probably what I'll do is actually next week I'll hand out the problem set maybe on Tuesday instead of Thursday, just to give it a little extra time so I can make it longer. Good. Okay. See you next class.